All right, Pumas. We're going to start off the second semester, Unit 3 on radicals. So this unit, we're going to learn how to solve radical equations, graph radical functions. We're going to learn something called the rational exponents when the exponent's a fraction. Um, but before we do any of that, we got to make sure that we can simplify radicals. We're used to square roots, but now we're going to start looking at nth root radicals. So it could be the cube root, the fourth root, the fifth root. Not necessarily, we're just not limited to the square root anymore. All right, so we're going to take a lot of the concepts that we've already learned about square roots and apply them to the nth root. And so, again, just a quick reminder to use this feature over here, send it to your Google Drive where your notes are saved, and you can always access them. All right, so just click on that, pick your address and hit allow, and then you'll get a copy of all your work. All right, so why do we need radicals? All right, so in Algebra 1, you guys were first introduced to radicals when we were solving quadratic equations. So you had an equation like x squared equals 25. You'd square root both sides of the equation to solve for x. You would get x equals 5 and x equals negative 5. Because, again, negative 5 squared is positive 25. And so that's where we were kind of introduced to square roots first time. And again, you saw them again in geometry when using the Pythagorean theorem to solve the missing side of a right triangle. All right, once you add up the two and it's find the hypotenuse, you'd have to square root it, or any of the sides you had have taken a square root to solve. All right, so we saw radicals again there. And little history, radicals there, the square root, it's kind of the first time someone identified an irrational number. Pythagoras was a believer that there was only integer numbers. And when he used his theorem, he was getting numbers that were not whole numbers. And so this was very confusing for the early mathematicians on what happened here. When using the Pythagorean theorem, they would get rad2, and they didn't know what that meant, what that was, what kind of number it was. So they discovered irrational numbers through radicals. And then as we learned last unit, right, taking the square root of a negative leads to imaginary numbers. So radicals are responsible for identifying two different types of numbers, right, irrational and imaginary. In stats, again, you guys have not taken a stats class yet, but you've done some basic stats in middle school and stuff. There's something called the standard deviation that requires us to do square roots. And when you get to advanced stats, radicals help you to lower the variance when you're creating models to predict financial markets or anything like that. It just helps to lower the variance. So using radicals, it's critical to your numerical literacy. And now that we've studied polynomial functions last unit, so that's right, cubic polynomials, fourth degree polynomials, right, something other than quadratics. Now we're going to have a need for something other than just square roots. All right, so this is a higher index than 2 here. What's an index? It's the root. So like if I want the cube root, like an example right here, okay, the cube root of 8, 3 is the index number. So what is the cube root of 8? It's 2. Well, how do we know that? Because 2 cubed, right? If I asked you what is 2 cubed, right, we would know that that is 8, right? 2 times 2 times 2, right, equals 8. So when I want to do the inverse of that, cube root of 8, I get 2. All right. So that's there. All right. All right. Okay, so we call these the nth roots. So Instead of just the squared root, because it could be any power, right? So if it's something raised to the fourth power, I'm going to use the fourth root to undo it. If it's something to the eighth power, I'm going to use the eighth root to undo it. So the nth root of a real number a can be written as the radical expression nth root of a, where n is the index. Okay, so the n, the root, whatever we're doing, we call that the index number of the radical, and the a, the number inside the radical, is called the radicand. Right? When there is no index number, so if you don't see an n there, that small little n, it is implied that the index number is 2, so a square root. So we've never written a 2 there before, but we've always done square roots. So when there's no number, it's implied that we're doing the square root. All right. When you are simplifying, okay, the radical sign indicates the principal or positive root, okay, not solving. Remember, when we're solving, if you like x squared equals 25, you're going to get 5 and negative 5. But if it's just what is the square root of 25, it's just 5. If I want a negative 5, I would put what is the negative square root of 25. When we're simplifying, whatever the sign in front of the radical is, that's what we're going to use. All right. And we'll see that if it's an odd index number, you could also do negative roots for odd index numbers. All right, so here it says translate each radical expression to solve a verbal description. Okay, so in this problem here, right, says the cube root of negative 27. So this is asking us what number raised to the third power is equal to negative 27. Okay, and so that's going to be negative 3. All right, so right, if I wrote that out, right, negative 3 times negative 3 times negative 3, right, you would get negative 3 times negative 3 is 9, and then 9 times negative 3 is negative 27. All right, so the cube root of negative 27 is negative 3. All right, so notice it wasn't imaginary. Even though there's a negative inside the radical, it's not imaginary because this is an odd index number. All right, which means I can do the radical of a negative number. But if it's even, it'd be impossible to do that. So whenever you have an even index number, you cannot take the root of a negative number if the index is even. All right, only if it's odd. And then your principal root there is negative 3. So if there was a negative out in front, then that would have turned it to a positive 3. All right, so what does this mean right here? Well, this is going to be a little bit tougher to figure out, but what's it saying? It's saying what number raised to the fifth power is equal to 1024. And the fifth root of 1024 means what number raised to the fifth power, okay, is 1024. So that one's a little bit harder to figure out. It's going to end up being 4. All right, and so if I did 4 times 4 times 4 times 4 times 4, all right, we're going to get 16. We get times 16 times 4. All right, 16 times 16 is 256. 256 times 4 is 1024. All right, so these numbers get big really fast here. So gotta know our perfect squares, our perfect cubes, and so forth. You could always use prime factor tree as well to help us here. We'll take a look at that a little bit later. All right, hit submit, and it takes you to the next page. So here, this is just for your viewing pleasure. I would screenshot this or write it down. When we're in class, if we're in class, I would let you use this table on tests and quizzes. It's just the first 11 perfect squares, the first 11 perfect cubes, the first 11 to the fourth power. So these are our perfect powers, okay? Squareds, cubes, and fourths. Again, you should know, obviously, your square roots. You should all know those. You should know the first couple cube roots, first couple fourth roots. But it's going to, right, if you have this table in front of you, it's going to make simplifying a little bit easier. as we know, one of our strategies is to look for perfect squares or perfect powers that go into a number. All right, so down here in print, that's what it says. Knowing these perfect powers will help when simplifying nth root radicals. When simplifying an nth root radical, and it's not a perfect power, you are dealing with an irrational number. So we've seen that before, right? So if I said the square root of 40, right, it's not a perfect square. So that's going to be an irrational number. We can still simplify it, but it's not, your answer is not going to be an integer. All right. And down here, a little bit more detail when dealing with an even root, okay, square roots, fourth roots, sixth roots, eighth roots, okay, when dealing with an even root, you cannot have a negative radicand, meaning the number inside cannot be negative. If it is, we're dealing with an imaginary number, all right? But when dealing with an odd root, so cube roots, fifth roots, seventh roots, right, you can have a negative radicand, okay? The result is just a negative principal root, all right? So this is for your notes. You could write them down. All right, screenshot that. That's a good little tool to have. All right, so let us look, just quick review, two different strategies of simplifying radicals. All right, we're going to use perfect square factors, and we're going to use the prime factor tree. All right, so if I said simplify the square root of 24, okay, the first strategy, one I like to use, is just what is the largest perfect square factor that goes into 24? And you write it down. Right? It's 4 times 6. 4 is the perfect square. And then so if you put square roots on that, you haven't changed it, right? Because when you're multiplying radicals, as long as it's the same index number, you can multiply them together. 4 times 6 is 24. Why do we do this? Because we know the square root of 4. The square root of 4 is 2. So that goes away, and then the rad 6 just stays rad 6. Right? And so we could simplify square root of 24 to be 2 rad 6. This is the simplified version of this irrational number. And that's what our goal is in a math classroom, is to write our answers in the most simplified version so we create that one unique answer for us. All right, and then square root of 24, different strategy here is the prime factor tree. So just choose anything that multiplies up to 24. Okay, so you could start with 8 times 3. You could have done 2 times 12, right? And once it's prime, you could stop. But 8, okay, I got to keep going. 8's 2 times 4, okay? And then 4, I could keep going. So 24 as a prime factor is 2 times 2 times 2 times 3. Right? So what we're looking for when we're doing square roots, remember the index number here is 2. We don't write it when it's 2, but it's 2. I'm looking for doubles. Does any of these prime factors show up twice? Right? And so the 2 does. It shows up 3 times, but we only care about doubles. All right? And so if it shows up as a double, okay, that's going to be means we could do that square root. There's 2 of them. So that there's going to be a 2 involved. The 2, okay, is going to be a factor on the outside of the radical, because we actually did the square root of that. And then what's not a double goes in. So 2 times 3 goes inside the radical, so it's 6. So you can see that both answers are the same. Okay, so which way is easier? It's up to you. Again, if you know your perfect squares, probably this first way is a little bit quicker. But as we're going to see, we're going to do cube roots and fourth roots, and those we don't know our perfect fourth roots as well as we know our square roots. So this prime factor tree method is going to be a good tool. All right, so let's do the same thing for cube roots. Okay, so the cube root of 24. All right, so if I know my cube roots, okay, that table that we had, I knew that 8 was a perfect cube. Oops. Do that, change my font size. Okay, so I could rewrite 24 as 8 times 3. All right, put a cube root on both of those. Don't forget the little index number. And the cube root of 8 is 2. Again, I chose 8, okay, times 3, not 12 times 2, because 8 is a perfect cube. So cube root of 8 is 2, and then the cube root of 3 just stays cube root of 3. All right, so if I had to simplify cube root of 24, it's 2, okay, times the cube root of 3. So this would be my answer. All right, now using the prime factor tree, All right, same idea as before. Let me just start with different numbers to show you it doesn't matter. So if I could do 12 times 2, all right, and then 12 is 6 times 2, all right, and then 6 is 3 times 2, right? So again, all these prime numbers right here, those are my prime factors. I have 3 2's, so 2 times 2 times 2 times 3, my prime factor list. And now, because it's the cube root, I'm looking for triples. Does any number show up 3 times? All right, and so 2 shows up 3 times. So that's the factor, that's the perfect cube factor that's going to show up on the outside of the radical. And then whatever is not does not show up 3 times, okay, stays inside. And again, if there's more than one thing, you just multiply it together. Okay, and so we get 2 cube root of 3, which matches up before. Again, now since we don't know our perfect cubes as well, now maybe the prime factor tree is a better strategy. All right, and we just do it and we look for something that shows up 3 times. If no number shows up 3 times, that means you can't simplify it. Then you would leave it as it originally was. All right, if 2 numbers show up 3 times, then you would multiply. So say there was 3 2's and 3 3's, you would multiply 2 times 3 out in front. All right, so there's our first look at simplifying a cube root. All right, and this summarizes it. Okay, how do we simplify an nth root radicals? Right, so if you know the perfect nth power, you can identify the largest perfect nth power factor and simplify by putting the nth root of that factor outside the radical sign and leaving the other factor or factors inside the radical sign. All right, so again, if you're looking at square roots, if you know the perfect square factor that goes into it, you could just write it. So um, that's one strategy. The second strategy, okay, is if you don't know the perfect nth powers, okay, you will use a prime factor tree and look for a prime factor that shows up n times. So again, if I'm looking for the fourth root, I need a prime factor that shows up 4 times. All right, so the n times is what we're looking at, whatever the index number is. Okay, whatever prime factor shows up n times will be put on the outside of the radical. Again, if more than one factor shows up n times, you will multiply them together on the outside. The prime factors that do not show up n times will be multiplied together and left inside the radical. All right, so here's some chance for you guys. All right, so pause the video here and you guys try these two. All right, so square root of 48, okay, I would go 16 times 3. Put a square root. Again, I chose 16 because it's a perfect square. Square root of 16 is 4, so it's 4 rad 3. Again, so I'm using that first strategy of finding that perfect square factor, the largest perfect square factor that goes into 48, okay, and using that strategy. All right, so now cube root, let's use the other strategy. Let's use the prime factor tree here. All right, so 54 is 2 times 27. All right, so again, if you know your perfect cubes, you may realize that 27 is a perfect cube. All right, but let's say we didn't recognize that, so we keep going, then that's 3 times 9, and then 9 is 3 times 3. All right, so what are my prime factors? It's 2 times 3 times 3 times 3. So does anything show up 3 times? My index number is 3, so I have 3 3's. Okay, so that prime factor is going to go on the outside of the radical. And then whatever is not circled here, right, the 2 stays on the inside. So the cube root of 54 is 3 times the cube root of 2. Okay, more you try, so go ahead and pause it and you try these as well. All right, so 450. Okay, so maybe I don't know the perfect square that goes into that one. That's kind of a big one, right? Maybe you do know that 225 is the perfect square that goes into that. But let's say we didn't. Okay, so I'm going to use the prime factor tree. So it ends in a 0, so let's go 45 times 10. And neither one of those are perfect squares, right? So we just got to keep going. So 45, okay, is going to be 9 times 5. 10 is 2 times 5. And then 9 is 3 times 3. So this prime factor tree, okay, is going to be 2 times 3 times 3 times 5 times 5. All right, and so I have, that's my prime factors. I'm looking for doubles. Remember, that if there's no index number, it's implied that it's a 2. So I'm looking for doubles. So I have 2 sets of doubles here, right? 3 shows up twice and 5 shows up twice. So both of those are going to be pulled outside. A 3 is going to be outside and a 5 is going to be outside. So you multiply those together, right? Because these are all factors. So 3 and 5, so 15 on the outside, and then the 2 stays on the inside. Again, if you knew that 225 times 2, 225, the square root of 225 is 50. So you could have got there using 25 as well. All right, so 270. Okay, now let's do cube root. So now I'm going to do the prime factor tree. I'm going to look for something that shows up 3 times. Or maybe you notice something. 27 times 10. And we just did 27. 27, cube root of 27 is 3. So maybe I could just throw my cube roots back on it and use this strategy this time. Cube root of 27 is 3, and then so it's 3 cube root of 10. All right, so if you recognize a perfect cube or a perfect square, then you could use that strategy as well, or continue to prime factor tree it. All right. Simplifying radicals, okay, nth roots of algebraic expressions. So now we're going to get variables in here. All right. So what do we do when there's variables involved? All right. So I want you guys to use the text feature. I'll do it here in the video, but in class you'll be using the text feature to type in what you notice about all these examples up here and what you're still wondering. To help you answer the what you're still wondering question is, what don't these examples show us? All right, so right here we have, right, the square root of x squared equals x. Okay, square root of x to the fourth equals x squared. Again, so you're asking yourself, what number times itself, what variable times itself equals x squared? So x times x is x squared. So the root of x squared is just x, right? And then x cubed times x cubed would be x to the 6. Remember our properties of exponents, right? You add exponents when you're multiplying. So, right, for all these square roots right here, I'm noticing that the answer is just half of that original exponent, right? X to the 16th, 16 divided by 2 is 8, right? Because if I multiplied x to the 8th times x to the 8th, I would get x to the 16th. Okay, looking at cube roots, right? Cube root of x cubed is x. Cube root of x to the 6th is x squared. Okay, cube root of x to the 9th is x cubed. Cube root of x to the 27th is x to the 9th. What are we noticing here about my answers? Now, again, now it's a third of all those x. I'm dividing by 3. Over here, I divided by 2, because that was the index number. Here, I'm dividing by 3, and I'm getting the answers. Let's see if it's true for these other ones over here. So if I divide by this index number, okay, so 16 divided by 4 is 4. So x to the 4th, my new exponent is just that, right? 30 divided by 5 is 6. And so the 5th root of x to the 30th is x to the 6th. Right, if I multiply x to the 6 times x to the 6 times x to the 6, x, right, you add up the 6's 5 times to get 30. So what am I noticing? Okay, so I'm noticing that, okay, we are dividing exponent by the index number, right? And that gets us our new exponent. And the variable stays the same, the base, right? The base of x doesn't change, just the exponent changes. All right, and so I mean, this goes back to a lot of our properties of exponents that we learned in Algebra 1. So we'll probably have to do a review on that as well. So look for an Edpuzzle on that. All right, so we just divided that. That's pretty simple, right? So I could do any nth root okay, of any variable by simply dividing, okay? But what's different here, okay, is all these happen to be perfect factors. There was no remainders, right? So I'm wondering, what if there's a remainder, right? What happens, okay? What if there is a remainder, right? What's going to happen to that remainder? So that's something that we need to take into account because all these, right? I didn't do anything like x to the cube root of x to the 25th, right? Because 3 doesn't go into 25 evenly. All these I made sure they were even so we could see that pattern, okay, that we're just dividing. All right, so we're obviously going to have to address this still because it's not always going to be perfectly even. All right, so let's try to make a connection between what we did with numbers, okay, and see if it will make a connection to what we do with variables. So over here we have cube root of 54. If we do the prime factor tree, we get 2 times 3 times 3 times 3. Triples, right? So we pull out that 3, we get 3 cube root of 2. That leftover factor stayed inside. So what if I rewrite x to the fourth, okay, as x times x times x times x. So I got 4 of them there, right? That's, you guys all agree that's the same thing. So using what we know is we're looking for triples. So if I have 3 x's here, that means I could put an x out in front. Okay, and then what's left on the inside, just like this 2 was left on the inside, this x is left on the inside. So x, now again, I want to be a little bit neater on my handwriting there so you guys see that that's the index number. It's not x cubed on the outside, it's just x on the outside. That's the index number, cube root of x. So just like with our numbers, right? If it showed up 3 times, it went to the outside. If it didn't, it stays on the inside. So x to the fourth, you can write it out. It's 4 x's, you get the triple, and that leftover one stays on the inside. All right, so that is how we can do that. But are we going to want to write it out like that? If it's like x to the 25th, are we going to want to write down 25 x's? Right? Or can we make a connection between, we know multiplication, division, how it's repeated, that we can use division instead of writing it all out. Okay, so let's take a look at what I mean by that. So here we got some square root of x to the ninth. Right? So if you rewrite it as x to the 8th times x, right, that's still x to the ninth, but I separate it because now, right, I could do the square root of x to the 8th. All right, and so that's just x to the fourth, right? Remember, we just divide, and what's left is that rad x to the fourth times x. So if we divide 9 divided by 2, right, 9 divided by 2 is 4 with the remainder of 1. Where do you see that 4 at? That 4 is the new exponent on the number outside. Okay, let's see if that's true for this one as well. So 25 divided by 3 is 8 with the remainder of 1. So 8 should be my exponent on the outside, all right? And my remainder of 1 should be my exponent on the inside, right? And so that's what we got. Again, you could separate it, okay, to the largest, multiple of 3 that goes into 25 kind of type of thing, or you could just do the division. Right, 25 divided by 4 is 6. So I should have my exponent on the outside should be 6, remainder of 1, so x to the 1 on the inside. All right, now let's look at an example where the remainder is not 1. So 11 divided by 4, right, is 2 with the remainder of 3. So 2 on the outside, x squared on the outside, right, and then x cubed on the inside. Right? And it's the fourth root. So here I can't simplify anymore because the index number is bigger than the exponent. So obviously 4 does not go into 3. All right, so it is okay to have an exponent still left on the inside if that exponent is smaller than the index number. Right? You should never have an exponent that's larger than the index number. If you do, it means you didn't simplify it enough. All right, and so over here I kind of just described that. To simplify an nth root radical of a variable expression, you divide the exponent of the variable by the index number n, right? So Index number was 3, we divided by 3. Index number was 4, divided by 4. All right, the quotient, so how many times it goes into it, is the new exponent on the variable that is outside of the radical, and the remainder, right, what's left over, is the new exponent on the variable that is inside the radical. If there is no remainder, then there will be nothing left inside the radical, as we saw on the previous page when everything went into it evenly. All right, and there we go. That's how we simplify variable expressions. All right, let's put it all together now. So what if we have numbers? What if we have more than one variable in there? Okay, how can I do it? So one strategy is to separate everything. All right, I could separate this as the square root of 75 times the square root of x to the 7th times the square root of y to the 4th. And then we just simplify each one of those and then put them back together. So 75 is 25 times 3. So that's 5 rad 3. Square root of x to the 7th. Again, remember the index number is 2, so I just divide, right? So that's going to be x cubed. 7 divided by 2 is 3, so 3 on the outside with a remainder of 1, so x on the inside. And then y to the 4th, okay, square root, so just divide, that's just y squared. There's no remainder, so there's no radical. Right? Then I just put these back together. These are being multiplied. All right, so you multiply the outsides together, you multiply the insides together. So on the outside, I'm going to get 5x cubed y squared, and on the inside, I get 3x. So I just separated each of them separately, and then I put them back together. All right, so really the hardest part is the numbers. The numbers are actually take more work, a little bit harder to simplify than the variables, because the variables you're just dividing whatever the index number is. Divide the exponent by the index number, right? Remainder stays on the inside, the quotient goes on the outside. All right, so if we do another one, now we have a cube root. So now I'm going to be dividing the exponents by 3, but I've got to do the cube root of 40. All right, so if I separate it, okay, cube root of 40 times the cube root of x to the 5th times the cube root of y to the 11th. All right, so the cube root of 40, that's going to be 8 times 5. Again, I chose 8 because 8 is a perfect cube. All right, the cube root of 8 is just 2. So that's 2 times the cube root of 5. And then I divide right here. 5 divided by 3 is 1. So it'd be x to the first power, which I don't have to write, okay, times the cube root of x squared. The remainder was 2. So there's an x squared on the inside. All right, 11 divided by 3 is 3 with the remainder of 2. So y to the third on the outside, cube root of y squared on the inside. As you can see, right, especially writing with the mouse, it's hard to see. Make sure you understand that's an index number, not an exponent on the outside. So just try to write it neat to keep track of that. Okay, so on the outside, I have 2xy cubed. So 2xy cubed on the outside. All right, now I have my radical sign. My index number is 3. Now on the inside, I have 5x squared y squared. And I just put everything back together. I just multiplied it all back together. Separated it so I could simplify each one, and then I put them back together. All right. And again, if you can do this without separating it, that's fine as well. All right. Maybe you have to work on the number, do your prime factor tree or your perfect factors, your perfect power factors, right? And with the variables, it's pretty easy. You're just dividing. All right. I want you guys to try this one, so go ahead and pause the video and try it, and then check your work. Okay, so 24 cube root of 24, that's 8 times 3. Again, let me separate it. I'm just separating it right now. Again, the step is not necessary, but as a beginner, it's good to see. So 24, right? That's 8 times 3. Put the cube roots back on it. So the cube root of 8 is 2. So it's 2 cube root of 3. And then 6 divided by 3 is 2, no remainder, so just x squared. And then same thing over here, just y squared. All right, so there's no remainders there. So I just put it back together. So on the outside, it's 2x squared y squared. And then that's cube root of 3, the only thing on the inside. All right, and that's how you would do that one. Okay, last example here. Okay, so 5th root of 256, okay, u cubed v to the 6th. Okay, so if I separate this, oops, make my pen smaller. All right, so if I separate this, I get the 5th root of 256. Okay, so I'm gonna have to do some work here. All right, and then I've got the 5th root of u cubed. That's kind of unique because that means we can't simplify it because the exponent's already smaller than the index number. And then 5th root of v to the 6th. Okay, so let's start with 256. Okay, 5th roots, maybe I don't know any of my perfect 5th roots. I mean, 2 to the 5th is 32. All right. But after that, I mean, 3 to the 5th, you're getting pretty big there now, 243. So I'm just going to break this down. I'm going to have to use the prime factor tree here. All right, so 256, all right, that's 16 times 16, which is 4 times 4. So it's going to be a lot of 2's in here. It's going to be 8 2's. 256 is 2 to the 8th. Okay, so I'm looking for something that shows up 5 times, which I do have, and then I have 3 left over. So this is going to be a 2 on the outside, and then in the inside, multiply those together, 2 times 2 times 2, it's 8. So that's 2 times the 5th root of 8. Okay, this one I cannot do anything with. And then this one, 6 divided by 5 is 1. So I get a v on the outside, and there has a remainder of 1, so a v left on the inside. Put it all together, what's on the outside? I have a 2 on the outside and a v on the outside. And what's on the inside? 8u cubed times v. So that will be my final answer. All right, and so now we've got some good examples to look at. And then you understand why we need radicals, why we have these nth roots, where they coming from, and then how to do it. So there you go. Hit submit on the last one. Again, now if I go into my Google Drive, that'll be there in my Google Drive because I sent my notes there. All right. Thanks for watching.